We can start. Okay, so you got cylindrical coordinates due tonight at 7. Written homework due in recitation tomorrow. And we're rolling. We got our next exam a week from Friday. So I'll post study materials before the weekend if you want to get going over the weekend. And so if the exams haven't been going as well as you'd hoped, then my number one suggestion would be start preparing earlier, and then work on it in many sittings, and then on Tuesday, Wednesday, Thursday, get in to my office and ask questions about all the review problems that you're doing. Okay. So that's the number one thing, is to get studying earlier so you have more times to sit down and look at it, and don't wait till the last minute to prepare. Okay, so we saw cylindrical coordinates wasn't really much new, because we talked about polar coordinates and added z to it, and so we'd kind of done it before. We're just formalizing it under the term of cylindrical coordinates. So there's another system called spherical coordinates, and this is a different animal. This is new. Okay. So spherical coordinates the base coordinates are rho, phi, and theta. Is it phi or phi? Okay, you're saying phi, so I will try to say phi. I've probably gone back and forth a million times. So I heard phi, so we'll go with phi. All right, so it's rho, phi, and theta. Okay, so we're going to start with theta. Theta is the same trig angle that you've been dealing with for years, right? So it's this, and in this course, same standard trig angle. And what is that? It's the angle swept counterclockwise from the positive x-axis. So that's what I'm showing with this gray kind of semicircle here. So theta sweeps so this is theta equals 0. We sweep counterclockwise in the xy plane. So the positive y-axis is pi over 2. The negative x-axis is pi. The negative y-axis is 3 pi over 2. And then back to 2 pi. Okay, so that's the same. Then we have this another angle. So there's phi and theta are both angles, and then rho is the distance. Okay, so theta is the standard trig angle. Phi then is in the direction of theta. It's the angle swept down from the positive z-axis. So theta determines the direction you're gonna go. So this is what phi looks like. So here I'm at this angle here, somewhere in the first quadrant. So there's pi over 2, somewhere in the first quadrant here. And then once theta is determined, then phi is the angle swept down in the direction of theta from the positive z-axis. You see that? So it could be in any direction. Whatever theta is, you're going to tip down from the positive z-axis in the theta direction. So phi is angle measure tipped down from positive z here's the key, in the direction of theta. In the direction of theta. So that might point to your left. That might point towards you. That might point, in this case, kind of towards you and in front of the screen. That might point back into the right. So that's what makes this much different. These coordinates are based on two angle measures, and this angle phi is probably something you've never seen before. Okay, theta is their standard trig angle, and then once you pick theta, you sweep down in the direction of theta from the positive z-axis, and that's the angle phi. So theta, again, normally 0 to 2 pi. Okay, there's probably exceptions, like maybe a negative pi over 4 or something like that, but normally 0 to 2 pi. So then phi, though, there's no exceptions to this. Phi, the starting value of phi is 0, and then what would the greatest value of pi be that would make sense? We need to get below the xy plane too, right? So from 0 to pi. And phi equals pi is, how would we describe phi equals pi? What would that be? Negative z-axis, no matter what theta is, right? Doesn't matter what theta is, once you get to pi, now you're pointing straight down. So let me show you that. So here for this angle, so here's increasing phi from 0 down to pi. Now that is non-negotiable. Your angle phi will always be from 0 to pi. And then rho, so once you've picked your theta and once you've picked your phi, then once you picked your theta, once you picked your phi, then the rho is the distance from the origin. So rho then is, now that you've got the direction from the origin, it's the distance from the origin. Again, this is positive. Rho is, so this is distance from the origin. And why did they pick Greek letter rho? It's because of the R, stands for radius, right? So this is like the radius of a what? Sphere. That's what's called spherical coordinates, because it's based on rho, which is your like radius out from the origin. And this is going to be greater than or equal to 0. We will not see negative rho values. We will not see negative rho values. You could conceive of it that it would be in the opposite direction, but I've never seen it. So the order that you think about generating a point would be theta, and then phi, and then rho. So in terms of the way you think about it, it's theta, then phi, then rho, but ordered pairs are listed as rho, phi, theta. It's just the way they do it. Okay, so normally an ordered pair will be listed as rho, phi, theta. But you really think about generating a point in the opposite direction. Theta first, then phi, then rho. So here I'm showing theta as 0.847. That's in the first quadrant. Phi is 0.7693. That puts us in the first octant. And then rho is 0.875. And so then we get, for those three coordinates, we get that point right there. And then so you can see how you could get every point in R3 with these three coordinates. With the two angles and a rho, you could locate any point in R3 this way. So what I want you to do is think about what would this be? Theta equals 2 pi over 3. So what set of points in R3 would you get for this? Phi equals 3 pi over 4. These are three separate questions. Rho equals 2. Three separate questions. For each of these, what set of points? Describe the set of points that you would get. Theta equals 2 pi over 3. Astrid, how did theta equals 2 pi over 3? How do you describe that? What is that? Huh? Okay, so the circle is just the way that I've kind of displayed it. That's not that that circular arc is not where it ends, right? So it's just kind of for visualization's sake that I've made that like a half circle. So, but really, what's that? Yeah, so it's just gonna, in the direction of that semicircle, it's just gonna extend infinitely. So like a rectangle would be maybe a better way for you to conceive it, but it just keeps going on forever at 2 pi over 3. So that's gonna be close to, yeah, just a little bit greater. That's somewhere around there. So something like that. That's theta equals 2 pi over 3. And so we call it like a half plane, right? And the direction away from 2 pi over 3, it just extends infinitely. It doesn't stop with this half circle. That's just kind of the way that I'm helping you see it. Are we cool on that? All right, what about phi equals 3 pi over 4? Eddie, what do you think about that?
Like a cone.
A cone? Tell me about it.
Points downward, like in the negative z direction.
Okay, so a cone, so it ends up being a half cone. That's exactly right. So it's going to be, if I could show it here, let's turn this off. So if phi is 3 pi over 4, what is that? 9, something like that. So if you imagine what you would get for all thetas there, when you get like a cone down there. You see that? Can you imagine that? I guess if I just type it in, we would get it. Let's see here. Look at that. There it is. Phi equals 3 pi over 4. Okay, what about rho equals, are we good? Any questions? Rho equals 2. Yeah, him. What's that? Hollow sphere. So all spheres are hollow, because you just, when you say sphere, you just mean the shell. So it is a sphere. So if it's filled in, then we call it a ball. Okay. But yes, it's a sphere. Exactly. So if it said rho equals 2, doesn't like that. Oh, I think r equals 2. There you go. Yep. So thus, spherical coordinates, because a constant value of rho gives you a sphere centered at the origin. That's better. Yeah. Yeah. So this is the reason why it's spherical coordinates. Just like in cylindrical coordinates, a constant value of r, right? R was our distance from the z-axis, gives you a cylinder. So with a constant value of rho, you get a sphere. Thus, spherical. So spheres are very well suited to this coordinate system. Sphere is centered at the origin. Okay, any questions on those examples? Good? Okay, so let's talk about the relationships now. So now we've got rho and phi are these new variables in R3, and so we have x, y, z, r, theta, rho, and phi. So it's like 7 variables. Let's see what all the relationships between all of those are. So here's just a generic value of rho, phi, and theta. There. A little further, not too far. That's good. Okay, so here's this generic rho, phi, and theta. Some more room. There we go. Okay. So what we're going to do is draw some triangles here. I'm going to drop straight down into the xy plane. And then from there, I'm going to go straight to the origin in the xy plane. Best lines I've drawn all day. So this is a right angle, right? And then from here, I'm going to draw this. That's the worst line I've drawn all day. And that. Okay, so I want you to, given these pictures, so this is a right angle here. So I want you to, in this diagram, identify x, y, z, r, theta, rho, what's that? So this one here?
Yeah.
That's x. Okay, where is y? Alyssa, Migler vector, where would y be? Coming across this way? All right, and then how about z? Andre, where's z? This one here? What do you think? We good? Good so far? Okay, what about r? Yanni, where's r? This one here is r? Agree with that? This one? So which is it? Is this r or is this r? So remember cylindrical coordinates. What did we say r was? Distance from the origin? So, no, distance from the z-axis, right? So it's like horizontal distance from the z-axis is r. So is it exhibit A or B? B. That's r. So if you wanted to, you could draw it up here, and it would be like this. This would be r. Also. That's also r. That's horizontal, right? That's a horizontal distance to the point. Okay, what's left here? Rho. What's rho? Kusi. What's that? But which? How would I label this diagram for rho? So this is our point we're talking about. It can be anything. It's not necessarily it's two. It could be anything. But what? How do I label this diagram with rho? Where do I label rho? How is rho shown in this sketch? This one? Yes. Okay. What about? I guess I skipped. What about theta? Where's theta? Already know where theta is. This one here? Is that theta? Yep, that's theta. And then what about phi? Where's phi? John?
The angle between like the diagonal line of the xy plane. Yeah.
So this right here, is this phi right here?
Yeah. Oh, sorry, in the x-axis.
This one. Okay. So if we wanted to put it in the triangle, where would it be in a triangle? So yeah, this is how we define phi, but then in these triangles, it also shows up where? The top? Yeah, up here. That's helpful. We want to have it see it there too. Okay, does this make sense? We got everything good? So we're going to write down our relationships here. So let's start with R, and we want to write R two different ways. So R relates to both triangles, right? R relates to both triangles. So in our triangles, our polar triangle there, what is R? Square root of x squared plus y squared. But in the spherical triangle, it's different. It's not a hypotenuse. So it's the hypotenuse in the polar plane, in the xy plane. But in the spherical triangle, it's not a hypotenuse. So we're going to use it. Look at this a different way. So what would R be in the spherical vertical triangle there? Rho, is it rho sine phi? Or rho cosine phi? Sine, right? Because if you said sine, you're right, because it's opposite, right? So rho is the hypotenuse, so then R is the opposite side. It's going to be rho sine phi. Everyone see that? So since R is rho sine phi, then we can use that to figure out what x, y, and z are in spherical coordinates. So using spherical coordinates now, so before in cylindrical coordinates, what was x in cylindrical coordinates? He wants r cosine theta. Agree with that? So now in spherical coordinates, we don't have r, so what do we have? So yeah, it'd be r cosine theta. But we don't have r in spherical coordinates. We have rho sine phi, right? It's going to be rho sine phi cosine theta, because this is r. And so then y is rho sine phi sine theta, because it's r sine theta, right? And then what about z in spherical coordinates? So z is this leg here. So using spherical coordinates, what would z be? Rho cosine phi. You see that? Because it's the adjacent leg to phi. Okay, and then we know that theta is this back to cylindrical coordinates, arctan of y over x. And then adjust if you need to, right? Because this will only give you an angle between negative pi over 2 and pi over 2. When you use arctangent, you might have to adjust to get an angle between 0 and 2 pi that you need. Okay, so then let's look at the other way here. So if we want to come up with, say, how can we write rho in terms of other things, right? So what's one way to write rho in terms of other things, other lengths? He wants r squared plus z squared. Does it work? Yes, square root, or we could just say r squared plus z squared. Okay, what's r squared? X squared plus y squared. So we could say x squared plus y squared plus. And why does this make sense? That's the equation of the sphere with radius rho, and that's what we said. Rho is like the radius, right? So this makes perfect sense. We got that from the triangle, right? The vertical triangle, and then r squared is x squared plus y squared. And lo and behold, we get the equation of a sphere centered at the origin with radius rho. Okay, so what about phi? I'm going to write phi in terms of other things. So it's going to be inverse trig function. So let's think about what makes sense. Arc sine, its range is negative pi over 2 to pi over 2. Arc cosine, its range is 0 to pi. And arc tangent also is negative pi over 2 to pi over 2. And thinking about phi, which relationship would make the most sense? Why is that? Yeah, because so we said the range of phi is from 0 to pi, and so our cosine would make the most sense, because then we'll never have to deal with adjusting the angle. We're always getting an angle between 0 and pi, and that's will be the value of phi. So our cosine of what? He wants z over r. Agree with that? So cosine is what? Adjacent over hypotenuse. So it should be z over rho, right? Adjacent over hypotenuse. And then if we want to write that all in rectangular coordinates, it'd be phi equals our cosine of what? Z over square root of. Right. So now that we got 3 different ways to express points in R3, that's lots of variables, and so we need all these relationships between them. This is like if you've got spherical and you want Cartesian. This is if you've got spherical or Cartesian and you want cylindrical. And this is if you've got Cartesian or rectangular or cylindrical and you want polar. Sorry, you want spherical. Okay, any questions on developing all those relationships? Okay, so you'll need those, but they should make sense, right? So yes, memorize them, but also be able to derive them. Like be able to create that picture and do it all from scratch, just because you understand what they are. Okay, so spherical triple integrals. Will look like what? So we're going to integrate over some solid E. It's going to be the same as what we've done before. We're going to integrate over some solid E. We're going to integrate some function of rho, phi, and theta. dv, but then so we saw with cylindrical coordinates that dv wasn't just dz dr d theta, dz r dr d theta, and so now we've got 2 angles and rho, which is a totally different thing. So the question is, what is dv? It's definitely not going to be d rho, d theta, d phi. It's going to be something else. So we have to figure out what the dv is. And we saw that what kind of changed things is when you're using an angle as a variable. So now we've got 2 angles as a variable, so it's going to be something quite different than just d rho, d phi, d theta. So let's going to figure that out. So any questions on any of these kind of base relationships? Our next step is to figure out what is dv in spherical coordinates. So let's do that. Can I erase everything? Okay, so let's put this down a little lower here. So to do this, we're going to draw a little element. So I'm going to do my best here. A little tricky. But at this point, we can think of a little dv element like this. See how this goes. Not bad. So this is our little dv element, right? And so we got to figure out what is, we're going to have, what's d rho, d theta, and d phi. It's kind of the projection of that thing in the xy plane. Okay, so what is d rho? And that little dv, d rho would be a little change in radius. So can you see what dimension on that little element that d rho would be? What would that be? What would d rho be? So I'll give you choices here. So would it be exhibit A, exhibit B, or exhibit C? D rho. D rho would be A, B, or C. You should be thinking B, right? So it's this, it's a change away from the origin. So this right here is D rho. Do you see that? Okay, and what is d theta? Where in this picture could we sketch d theta? Where in this picture would we sketch d theta? So first of all, is it a length on the element dv? Is it a little length on here? It's a change in angle, right? So where is d theta? On the projection, yeah, so where in the projection? Yeah, right. This right there, that's d theta. And so that d theta then, it allows us to find this dimension of the little element, this one right here. What does that equal? That little dimension. It doesn't equal d theta, but what? What's it? Not rho. So it's going to be r d theta. Just like, yeah. So that's going to be r d theta. But what is r? Rho cosine? Rho sine phi. So that's what r is. It's rho sine phi, and then d theta. Are we good so far? So that r d theta is really the same as cylindrical coordinates that we had, and that'll be that little dimension. Okay, so what's left is this dimension right here, here to here. So let's see if we can draw it. From there, back that way. What's that going to be equal to? So that has to do with what change? Change in phi, right? That's our change in phi. Is it d phi? No. So what would it be instead of d phi? Because d phi is just a change in the angle. So to get the length, add a radius of, what is that length right there? That's rho. So that little change in length at a distance of rho away is what would that be? Rho d phi. So the radius times the change in angle will give you that little length. Just like r d theta gave us that other little change in length. So now we got it. So volume is length times width times height. And we've got all those dimensions. We've got d rho was that first dimension we got, and then the second dimension we got was the width. Say, call that the width, which was rho sine phi d theta. Phi, sorry, rho sine phi, times the height. We'll call that the height. Rho d phi. Therefore, it equals, we got a rho and a sine phi and another rho. Rho squared sine phi d rho d phi d theta. So that's what our dV is for cylindrical coordinates. Did you catch all that? Ask me if I lost you. Ask, where did I lose you? Ask me. So these little dimensions, if they're based on a change in angle, then we need to multiply by the radius to get that length, right? The radius times the angle gives you the arc length. So that's what we're doing, both for the change in phi. We need to multiply by rho, the radius, to get that actual length right there. And then we saw that same thing for this change here. It was based on a change in theta. To get that little arc length, we need to multiply by r. So that's r d theta. But then in spherical coordinates, r is rho sine phi. So then we're just doing length times width times height. We're just using a little rectangular volume there. So it's just length times width times height. So then it's d rho times rho sine phi d theta times rho d phi. And that all together we get rho squared sine phi d rho d phi d theta. Okay, so let's try one. Any questions? Can I erase? Okay. So write the limits of integration for the bottom half of a sphere centered at the origin with radius 7. So we're going to integrate some function f over this solid, right? Over this solid. So that's a nice easy one to start with. So we're going to integrate over some f. So we need the limits of integration for this. So if we want the bottom half of a sphere centered at origin, radius 7. So normally the order we do is, so dV is what we just derived, rho squared sine phi. And what's going to happen, if we're actually solving the integral, what's going to happen to the rho squared sine phi? It gets multiplied by whatever function we're integrating. Again, this is a hypersurface in R4. Okay? And so then normally we do d rho, d phi, d theta. So we're going to do rho first will be from what to what? For the bottom half of the sphere centered at the origin with radius 7. 0 to 7. And d phi will be? So it's the bottom half of the sphere, which will start at the xy plane and go down from there. So our angles phi would be? Pi over 2, 2, pi. What does rho equals pi over 2? What set of points is that? Rho equals pi over 2. I heard the xy plane and the y-axis. Rho equals pi over 2. Sorry, phi equals pi over 2. So if I haven't specified theta, that means it's in every direction theta, right? Because phi tips down in the direction of theta. So if I don't specify theta, you're saying in every direction theta, if you tip down pi over 2, you get what? Get the whole xy plane, right? Okay, what about d theta? 0 to 2 pi. Does this example make sense? Okay, so the next one's just slightly harder, but not bad. So we want set up an integral in spherical coordinates, find the volume of solid consists of. So now I want to find the volume. I want to use a triple integral to find volume. Okay? The set of all points between x squared plus y squared plus z squared equals 6, x squared plus y squared plus z squared equals 9, in the third and fourth octants. Remember, the third and fourth octants are above the xy plane, above the third and fourth quadrants. So it's back here, upper left in the back, and upper left in the front. So see if you can do that. Number 2, go. So I want triple integral that gives the volume of that thing described. While you're working on it, I'll try to sketch it, okay? While you're working on it, I'll try to sketch it. Let's do d rho, d phi, d theta. So what was rho? Root 6 to 3. What do we think? From root 6 to 3. Good, okay? d phi. What will d phi be? Yeah. You want 0 to pi over 2. Agree with that? Nice. And then theta. Pi to 2 pi. And then if we want the volume of that thing, what will I integrate? Right, it'll be like 1. The function would be like 1, and then we'll have the rho squared sine phi. So when we do the math, rho squared, we'll be working on rho squared for antiderivative, rho squared sine phi.